Hello and welcome back to my channel. Today we're going to be talking about acceleration. So what is acceleration? Well, acceleration basically means a change in the rate of velocity. So you can write acceleration is the rate at which an object's velocity changes. So for example, let's say we have a car here. So we have a car, and it's not a very good car, but let's say we have a car here and it's traveling this way. At first, it may start off at maybe 5 meters per second, but then it's going to build up to maybe 7 meters per second, then maybe 10 meters per second, so on and so forth. And maybe it does all its acceleration or all its change in velocity in a time of maybe 5 seconds. So it does all that in 5 seconds. So these are different changes of velocity that the car is actually experiencing, right, over this period of time. So we call that acceleration. So similar to how you may be in a running position when you start, you might not be at your full speed as soon as you start, but you're going to slowly build up to it. So that's what acceleration is. The symbol that we use for acceleration is this A vector. Anything that has an acceleration is going to be a vector. So make sure you don't drop your vector sign, because we accelerate in a direction, right? Like if I got up and I started running and I started accelerating, I'm running towards something, or I'm running in a direction. So anything that has to do with acceleration has to do with direction. So the formula that we're going to use for acceleration is going to be A vector is equal to v2 vector minus v1 vector over delta t. And depending how you may have seen in the textbook, they might write it as vf or v final minus v initial I over delta t, but these mean the same thing. All right, vf, vi, 1, 2 initial, it doesn't really matter. They mean the same thing. Make sure you put your vector signs on all your velocities and accelerations, because everything has direction. So before we go further, I want to talk about dt and vt graphs, because they relate to acceleration and velocity in general, and are a key concept that we can touch on. So to begin, what is a dt graph? So I'm going to sketch it out for you. You have a d here, t here. A dt graph basically represents how an object's position changes over time. So dt graph, how an object's position changes over time. So basically it represents how an object's position changes over time. Some key features of a dt graph: usually if we have a more steep slope, that usually means that if we have a slope something like this, that usually means that the object has a faster speed or velocity, right? Let's say if we had a straight line on here, that typically means that there is no velocity, right? There's no, the object isn't moving at all. If we have an upward slope, like this one right here, that typically means that the object is moving in a positive direction. If we have a downward slope like this typically means the object is moving in a negative direction. Let's say you had actually a curved slope like this. This actually means that the object is accelerating. This means that the object is actually accelerating if you have a curve on your graph. How can we apply this to real life though, maybe? Well, for example, we can say maybe a person is walking, at a positive speed, but then they want to take a break in their walk. Then they want to start walking again and take a break again. Well, in this graph, this actually represents here the person maybe starting to walk and, keeping a constant speed. And then right here when the line goes flat, this represents the time where they stop walking and they have no velocity. Right here, we can represent that they're moving again, and here, them not moving. So this is how it can be applicable to a real life scenario. Now let's look at VT graphs. VT graphs. V and T. VT graphs. So what is a VT graph? Well, basically, when we're looking at what VT graphs are basically, they represent how an object's velocity changes over time. So unlike DT graphs, which represent how an object's position changes over time, VT graphs actually look at how an object's velocity changes over time. So what are some differences or what are some similarities? Well, again, here in a VT graph, if we have a steep slope like this, it typically means that the object has a high acceleration, right? If the object is moving again upwards, like this one right here, that means that it's moving in the positive direction. If they're moving downwards, it means they're moving in the negative. But one of the differences between a DT and VT graph is that on a VT graph, on the other one, when we had a straight line, it meant that the object wasn't moving at all. Here, when we have a straight line, the object is moving, but they're moving at a constant velocity. So if you have a straight line, it means they're moving at a constant velocity. So they aren't speeding up or slowing down, they're just moving at a constant velocity. And let's say if we had a curve like this, anything under this curve can represent the displacement of the person. But also if we take the slope of this graph, of a VT graph, we can actually find the acceleration. And with a DT graph, if we do take the slope of it, we can find the velocity. So some key differences we can look at between a DT versus VT graph. One of the differences that we can notice is that the slope on a DT graph basically means the velocity, whereas the slope on a VT graph is the acceleration. Another difference is that maybe how the straight line represents a constant velocity in a VT graph, whereas a straight line represents no velocity in a DT graph. Some of these little things are differences between DT and VT graphs, and you're going to see them when you're doing your fun work. And in questions all throughout this chapter, maybe you have to analyze some DT, VT graphs. But these are really the main concepts and some of the differences that you'll notice in VT and DT graphs. Next, we're going to move forward onto some problems that have acceleration in them and how we can tackle them. Okay, now we have some sample problems in front of us, and we try to work through them using velocity and acceleration, and what we know about what we're dealing with. So in the first question here, it says a car speeds up from 10 meters per second to 30 meters per second in 5 seconds. What is its acceleration? For this question here, it doesn't give us a specific direction. So we can just So we can just automatically set right as positive. Although it doesn't give us a direction here, in your textbook, it may give you a direction, and you want to make sure that you set your directions. One is positive and one is negative. You want to make sure you don't do the habit of not doing that, because you will end up with mistakes if you don't. But let's continue. A car speeds up from 10 meters per second, so we know that it speeds up from, so we know the v1 vector is going to be 10 meters per second to 30 meters per second. So v2 is equal to 30 meters per second, in 5 seconds. So our delta t is just going to be 5 seconds. Our required to find is the acceleration. So this one's pretty simple. We can just go A, and we can go A is equal to V1, V2 minus V1 vector over delta t. In this case, we already have acceleration on the right side. We're looking for acceleration, so we just have to plug in our numbers. So A vector is equal to 30 meters per second minus 10 meters per second over 5 seconds. A is equal to 20 meters per second over 5. And in this case, our acceleration will be 4 meters per second. And you might be wondering, second squared. The units for our acceleration are meters per second squared. You might wonder why it's squared. Well, if you go here and you go 20 meters per second and then put 5 seconds on the bottom, you may notice that the meters isn't on top, but rather on the bottom. So this isn't actually dividing, we're actually multiplying these together, and that's why you get seconds squared instead of seconds. That's an important thing to notice when we're doing these questions, to make sure you understand the units. In this case, it's meters per second squared, but it's something to keep in mind. The next question is, a sprinter accelerates at 2 meters per second squared from rest for 4 seconds. What is their final velocity? So here we actually have to do some algebraic manipulation to find out what the actual velocity is. So it says at 2 meters per second squared. So when it says meters per second squared, we can assume just by looking at the units that we're dealing with acceleration. So A is equal to 2 meters per second squared, and our delta t is equal to 4 seconds. So they accelerate from 4 seconds, but you might be looking at this and be like, oh my god, like we don't have their initial speed or something, or we're missing something. We only have 2 variables. But something that you have to pay really close attention to when you're reading these questions is some of the wording, like this one right here, from rest. When something's at rest, it means their initial velocity is 0. So in this case, we can assume that v1 vector is equal to 0. And that helps us out now. Now we're looking for v2 vector. Now this is a lot simpler. Now we can go analysis, and we can go acceleration is equal to v2 minus v1 over delta t. But v2 is 0, so we can just drop out that term completely, because that zeroes out. So we can put acceleration is equal to v2 over delta t. From here, we want to get this v2 up here onto the other side, so we can just multiply by delta t, and now we have acceleration times delta t is equal to v2 vector. And now we have our final velocity, and we can just do the solution. So we can go solution, and we can go 2 meters per second squared times 4 seconds. And again, you'll notice that in this case, the seconds is on the bottom. The seconds here will actually just cancel out with the seconds squared. So you're left with meters per second, which is the unit for velocity. And in this case, it will be 6 meters per second. And that we have the answer for that question. Let's look at this one right down here. Let's get rid of this line. So it says a train accelerates from 20 meters per second to 40 meters per second with an acceleration of 4 meters per second squared. How long does it take? In this question, we're actually looking for the time. So let's go, it accelerates from, so velocity v1 is equal to 20 meters per second. v2 is equal to 40 meters per second. With the acceleration, so it accelerates at 4 meters per. Realistically, on paper, you should really write it like this on top of each other, not to dash it out, because this is a better habit. you'll notice that you'll be able to pick up on units better, and it's easier to see when things cancel out. So you should really write it in this notation, not like this. Anyway, let's continue. So it says, how long does it take? So our required to find here is going to be delta t, right? So we can go analysis, and we can go A vector is equal to V2 vector minus V1 vector over delta t. Now we're trying to get delta t by itself, so we have to first get it out the denominator. A way we can get out the denominator and move it to this side here is by multiplying. So we can put our curly brackets here, multiply by delta t, and now we have A times delta t is equal to V2 minus V1. If you're wondering what happens to delta t on this side, remember, we're multiplying both sides by delta t. So if you multiply by delta t here, it cancels out the delta t on the bottom, and it multiplies by delta t here. So that's what happens to the other delta t, if you're wondering. Now we have acceleration times delta t is equal to V2 minus V1. Now we still want to get the delta t by itself, so we can just divide by acceleration. So now you're left with delta t is equal to V2 minus V1 over acceleration. And now we have time by itself. And now we can just go solution. So now we can go delta t is equal to V2, which is 20 meters per second, minus, V2 is 40 meters per second minus 20 meters per second over 4 meters per second squared. And you'll actually notice that the meters will all just cancel out, and you're only left with the seconds will also, all the units will actually match up to what you're looking for. So in this case, you'll only be left with seconds. So we can just go delta t is equal to, and in this case, you'll have 20 meters per second on the top, and you'll have 4 meters per second squared here. Because they're both on the bottom, the seconds will cancel out like that, and then the meters will cancel out, and you're left with seconds. And in this case, you have your final answer, is just going to be 5. So delta t is equal to 5 seconds. And that is how you use acceleration in these problems. Make sure to pay attention to your units, and make sure your units for acceleration are always meters per second squared, and you should always write it in this format to better help you when you're doing these questions. But that's my video on acceleration, including VT and DT graphs. Next time, we will be covering some key, equations that you're going to use with acceleration and all these different key moving parts. So see you then.